short explanation of expectation, also known as expected value. And we often have to work out the value of some sort of financial asset in the future, stocks and shares with uncertainty, or the likely winnings from a game of chance. And expectation is what we use for this. Expectation is a glorified word for finding the weighted average. We can use this not only in any distribution you come up with it, but we can use it to find the expected values of the standard distributions, and I'll show you a few later on. But let's start off with an example. Okay, so here's a gambling game. We're going to flip a coin, a £1 coin. If it comes up heads, you can have the coin. If it comes up tails, I get to keep the coin, and it's going to cost you 30p as an entry fee to play the game. Should you play? Well, we've got two outcomes. Head, you win £1, and the probability of that on a fair dice is 0.5. Or tails, you don't win, and the probability of that is 0.5. So what would you expect your winnings to be in this game? Well, we've got a 0.5 chance of winning £1, and we've got a 0.5 chance of winning nothing. We multiply those out and add them up, and we find that on average we would expect to win 0.5 of £1 or 50p. Yeah, this is called our expectation, or our expected value. Would we play the game? Yeah, yes, because the entry fee is 30p, so it'd be worth playing the game. We'd make a profit. So that 50p is our expected value or expectation. Yeah, and we calculated it using this formula here. And here's some notation. We write E for expectation in the brackets. It's the variable that we're using here. X here is our profit, is our winnings. Yeah, and we're just multiplying the winnings by the probability of those winnings. Yeah, you all notice that this is the classical way of calculating a mean. So basically we're using the same formula, aren't we? Hence, an expectation is just a weighted average or mean, and the weighting is the probability, isn't it? Probability weighting, yeah. Weighting. Here we go. Okay, so that's our fundamentals. We can use exactly the same approach for variance. We could find the expected variance, and we would do that by using this formula here. We need to find our expected value of x squared. There's our x squared, and then we already know our expected value of x because we worked that out our mean earlier, didn't we? And if you think about it, this is just a rewrite of our classic equation that variance is sum of our x squared times frequency minus our x bar squared times n, and because we're working in probability terms, that n is 1. There we are. So we're just basically doing the same thing. And just to make sure we understand our expected value of x squared, well, we're just getting our x squared and we're multiplying them by our probability, and then we're summing them all up. So again, it's just a weighted average of x squareds. So in this game, our expected value of x squared is our 1 squared times 0.5, and our 0 squared times 0.5 gives us 0.5. So our variance then is the figure from above, that 0.5, take away the mean squared, and then we found the mean earlier to be 0.5, so that's 0.25, and if we square root that, we get our standard deviation of 0.5. So here we are. So we've got a valid prediction of spread. Just to say, in effect, what we've just calculated is our expected value of variance, but presumably because that's too long, people just write variance for that. But in principle, we've done exactly the same thing, haven't we, in that formula. Now let's have a very quick run through how we can use this in standard forms, standard probability distributions. Well, let's have a look at a binomial. That's our probability and of a particular value r, isn't it? And what we're going to do is we're going to take each of our probabilities, multiply it by our value, and we're going to sum them all up. So the first one is 0 successes times the probability of 0 successes. The next ones we're adding to it 1 success and the probability of 1 success, 2 success, probability of 2 successes, all the way up to n successes and the probability of n successes. And that first term is going to be 0. Our second term therefore becomes our first and we've rewritten it just here underneath so we can see it. And as we can see in this form, both n and p are factors of each of these terms, so we can bring that out the front, put the rest in a bracket, and look, what have we got in this bracket? We're starting with q to the power n minus 1, ending with p to the power n minus 1, and everything else is a proper binomial expansion factor. So the bracket is actually p plus q to the power n minus 1, and of course in a binomial p plus q equals 1. Therefore p plus q to the n minus 1 equals 1 as well, doesn't it? And we get our classical result, the expected value of a binomial equals NP. We can do exactly the same thing approach with with Poisson, yeah, which is about queuing probabilities. So there's our probability. So we're going to multiply it out again. So we're going to get 0 successes or phone calls times the probability of that. 1 phone call times the probability of that. 2 phone calls times the probability of that. 3 phone calls times the probability of that. And that goes on forever, doesn't it? Because we can have an infinite number of phone calls. And as we can see here again, the first term is 0. Every other term has lambda and e to the minus lambda as a factor, so we can move those out front. And we effectively create an infinite series here. 1 lambda over 1, lambda squared over 2 factorial, 3 cubed over lambda cubed over 3 factorial, which some of you will recognize as the exponential series. So that is actually e to the power lambda, using that lambda in place of our x, and these two are just going to cancel out. And here we have our classical Poisson expectation. The expected value of Poisson is lambda. Okay, finally, here's our summary. So expectation or expected value is a weighted average, weighted by probability. There's our formula for it in its general terms, our variance version of the old classical. And we can also do this for any function of x. The expected value of the function g of x will be, we just put the g of x in place of the x in our equation up there and multiply it by our probabilities. And you can have a look at the discrete random variables, and that will show you a bit more about that on my video of that. So hope that's of use. Bye.